Good afternoon, everyone. I welcome you again to this next lecture of Dynamics of Machine, and we'll continue our discussion on the brakes. So, in the previous class, we have studied the block or shoe brake. Okay, simple block or shoe brake. In today's class, we'll continue with that discussion. So, let's start with pivoted block or shoe brake. Okay, in this case, the difference between simple pivoted block or simple block or this pivoted block is the angle of contact. In the previous case, the angle of contact was less than 60 degree. Okay, and this block was strictly attached to this lever. Okay, but in this case, the angle of contact is more than 60 degree. As you can see, that block, this 2 theta value of this 2 theta is more than 60 degree. All right, and this block is not strictly attached to the lever. It is pivoted on the lever. Okay, so it can move like this and this also. It can wobble around about this position. Okay, it is pivoted to this block. All right, so the only difference these are the main two differences, and the torque which will be produced, rest all are the same. That is, force P is applied over here. This Rn force will be acting in upward direction, and the Ft force will be acting in this direction when the wheel is rotating in clockwise. And if the wheel is rotating in anti-clockwise direction, the direction of Ft will also change. Okay, so everything is same. Only difference is, since this is more than 2 theta, so the this gives uniform wear of the brake lining in the direction of the applied force. Okay, so in the previous case, when the 2 theta was less than 60 degree, the pressure, the variation of the pressure was the uniform, and the force was acting normal along entire surface of the this block. Okay, but here the pressure is and the pressure is not uniform and the force is not normal, but the uniform wear will be happening along the lining of the brake. So it is very similar to what we studied in the case of clutches, right? And bearings also, that is uniform pressure theory and uniform wear theory. But we do not have to go in detail how these theories are working. We only have to find out the torque which will be applied, which will be required to apply the braking force. So in this case, the braking torque will be Ft into R, that will be same, that is mu dash into R into R. Okay, so this value of mu dash, instead of mu coefficient of friction, this mu dash is equivalent coefficient of friction, and it can be calculated by this expression, that is 4 mu sine theta upon 2 theta plus sine 2 theta. All right, so theta is again, it will be half of this 2 theta. Okay, and it will be given to you in the question, and mu is the actual coefficient of friction of the braking material. All right, so these brakes have more life and may provide a higher braking torque. Obviously, since the area is more, therefore the braking force which this will be applying will be more. Okay, so this is the major difference between the simple block brake and pivoted block brake. All right, now let's move on to this double block brake. So far we have studied only this single block was acting. Now here you can see that two blocks are applied for for the braking purpose. Okay, so when single block was applied to the rolling wheel, the additional load is thrown on the shaft bearing. So from that, from single block, the most of the force was transferred to the shaft bearing due to normal force, that is Rn. This produces the bending of shaft. Because of that, bending of shaft was happening. In order to overcome this drawback, the double block brake is also shown. So now what will happen? There will be two direction of Rn. Okay, normal reaction will be acting in this direction also and in this direction also. All right. It consists of two brake blocks applied in opposite ends of the diameter of the wheel, which eliminate or reduce the unbalanced force of the shaft. Right. The brake is set by a spring which pulls the upper end of the brake arms together. So this spring is over here, and as we push this downward, what will happen? It will try to bring both these towards each other. Okay, so this block will come in contact with this wheel and it will try to stop it. Okay, these are fulcrum by this point. All right. Now, when the current, this can be operated with the help of current also, or you can use electromagnet for this. This type of brake is often used on electric trains, and the force P is produced by electromagnet or solenoid, right? This force P will be produced by solenoid or electromagnetic force. When the current is switched off, there is no force on the bell crank lever. This is your bell crank lever, and due to uh, the brake is engaged automatically. So when the no force is acting, the brake will be engaged due to the spring force. So this spring will be pushing both the spring will be pushing this towards inside. Okay. In a double block brake, the braking action is doubled by the use of two blocks, and these blocks may be operated practically by the same force which will operate one. Okay, so the same amount of force will be required, and the braking torque will be equals to TB is equals to FT1 plus FT2 multiplied by R. Okay, so the since 2 Rn will be generated, so obviously 2 Ft will also be generated, and total will be taken their summation multiplied by this radius of the this wheel R. Okay, where Ft1 and Ft2 are the braking force on the two blocks. Okay, so this is how a double block brake works. Okay, now let's move forward to a band brake. Again, the band brakes are of two types, that is simple band brake and another one is differential band brake. So let's first go through this simple band brake. So as you can see, this is your wheel. Let me draw and show it to you. This is your wheel, okay, and this is the belt or the band. Okay, let me draw it with another color. Okay, this is your band. This black color. This is wrapped around this uh, wheel. Okay, so you might have studied belt and pulley drive, right? Open, it is very similar to open belt drive, right? So these are the two pulleys uh, which are transmitting power with the help of a belt. Okay, so one of the pulley would be this driving pulley, and another pulley would be the driven pulley, right? So generally this small pulley is the driving pulley. This type of arrangement you might have seen at different places where the floor mill is there, right? You take wheat and get it converted into the wheat flour. Okay, so this is the driving pulley, and generally we talk in terms of driving pulley. So the upper side of this belt is generally a slack side. This is little bit loose, and this lower side of the belt is tight side. So over here the tension will be acting T1, okay, and over here the tension will be acting T2. So always T1 is greater than T2. Why? Because the lower side is the tight side and the upper side is the slack side. Okay. So this, if this is rotating in clockwise direction, then this side will be T1 and this side will be T2. Okay. And if it is rotating in anti-clockwise direction, then also this lower side will be the tighter side and this will be the slack side. Similarly, over here also in case of belt drive you might have studied what is the uh, this angle of wrap, right? So the amount of portion on which this belt is in contact with the pulley, this is called as theta, angle of contact or the angle of wrap. Okay, and what is the relation between these two tensions? That is T1 upon T2 is equals to e to the power of mu theta. Okay, so I hope you remember these equations in case of, for the case of belt drive. This mu is coefficient of friction. This theta is the amount of angle of wrap, which is taken in radians, and T1 and T2 are the forces, tension forces taken in newtons. All right. So similar kind of thing is happening over here. So this is a lever, all right, and we will be applying force P at this end. Okay. So when this now consider this wheel is rotating in clockwise direction. Okay. and there is a belt which is wrapped around this wheel. All right. So since it is rotating in clockwise direction, therefore more amount of tension will be on this side, okay, and less amount of tension will be on this side. So the greater the tension, we call it as T1, and the smaller tension, we'll call it as T2. Now, as you can see over here, let me erase this and draw this again, that the belt is wrapped from here to here. Therefore, this entire angle is theta. This entire angle is theta. All right. And r is the radius of this wheel, and t is the thickness of the belt. Okay, small t is the thickness of the belt. All right. So it can be a belt or it can be rope also. It can be a leather band also, which will be used as a braking material. All right. Now, one end of the, I'll call it as belt. Okay. So one end of the belt is attached to this lever at point B, and another end of the belt is attached to this end of the lever, that is point O. And again, this point O acts as a fulcrum. That is, it is fixed at this point, and there is a uh, hinge over here. Okay, so this is free to move like this. All right. So this is a fulcrum point. All right. So I hope the diagram is clear to you. Again, this diagram is also similar. Only difference is in this, the wheel is rotating in anti-clockwise direction. So this will be T1. Okay, this will be tension T1, and T2 will come over here. Now the distance of this point where the T1 is acting from fulcrum point is B, and the distance of point where this force P is acting from the fulcrum point is L. All right. So again, we will be taking moment about this fulcrum point. So when the wheel is rotating in clockwise direction, this point P and this force P will tend to rotate this entire system in anti-clockwise direction. This tension T1, will tend to rotate in uh, clockwise direction, and this tension T2, since it is passing through the fulcrum point, therefore it will not produce any uh, moment. All right. So this is a diagram of simple band brake. Okay, let's just go through this text. A band brake consists of flexible band leather and one or more ropes, or a steel lined with the friction material. So it can be made of steel also with friction material, covered with friction material, which embraces the part of the circumference of the drum. A band brake is shown. It is a simple band brake. Okay, in which one end of the band is attached to a fixed pin or fulcrum O. Okay, so this O is the fulcrum point of the lever, while the other end is attached to the lever at distance small b from the fulcrum. Okay, so this band, one end of band is attached at point O, another band is attached at a distance b from point O, which is termed as capital B. When the force P is applied to the lever C, the lever turns about the fulcrum point O, and the tightness of the band on the drum, and hence the brakes are applied. So when we push this upside, what will happen? There will be tension T1 created in this band, and it will come in contact with this drum. So hence this this rotation will be brought to rest by the help of this tension. Okay. The friction between the band and drum provides a braking force. The force P on the lever at the lever C may be determined as discussed below. So T1 is the tension on the tight side of the band. T2 is the tension in the slack side of the band. All right. So just keep in mind, when it is rotating in clockwise direction, the T1 is over here, and when it is rotating in anti-clockwise direction, T1 is over here. Okay. Now let's move forward and see how it is addressed. So we know that the limiting ratio, as I told you in the previous slide, that the ratio between, or the relation between these two tensions, T1 upon T2 is equals to e to the power mu theta. Okay. And the braking force will obviously be T1 minus T2. Okay. Therefore, the braking torque will be torque. What is torque? It is force multiplied by distance. So the total force is T1 minus T2. Okay. And when it is multiplied by radius, it will give us the torque. Okay. And if the thickness is also considered, this thickness T is also considered, then we will take this as RE, radius as RE. All right. Now, considering the equilibrium of lever OBC, This is lever OBC, OBC. Okay. It may be noted when the drum is rotated in clockwise direction, as shown in figure A, the end of the band attached to the fulcrum O will be slack, that is loose. Okay. And the tension T2 at the end of band attached to B will be tight with tension T1. Okay. So when it is moving in clockwise direction, this will be the tight side and this will be the loose side or slack side. So at the tight side, the tension is T1 and at the slack side, the tension is T2. Okay. And as shown in when rotating anti-clockwise direction as shown in figure B, the tension in the band will be reversed. That is the end of the band attached to the fulcrum O will be tight with tension T1 and the other end will be slack with tension T2. Now taking moment about this fulcrum O, we'll take moment about this fulcrum O, this fulcrum O. So PL is acting in upward direction and T1 is acting in downward direction. So since T2 will not be producing any moment because it is passing through the fulcrum point. Okay, so P into L would be equals to T1 into O because T1 is acting downwards and P is acting upwards. Okay, and in this case, again P into L would be equals to T2 into P. So T2 is acting in downward direction, PL is acting in upward direction, therefore, and this T1 will not be producing any moment or couple because it is acting through the fulcrum point. Okay, so these are the equations, and L is the length of the lever from the fulcrum, that is OC, and B is the perpendicular distance from O to the line of action T1 or T2. So when the band brake is attached to the lever as shown in figure, then the force P must act upward direction in order to tighten the band on the drum. All right. So this is how we can determine the amount of torque which is required in case of a simple band brake. Now let's go towards the differential band brake. The only difference over here is the lever is extended. So one end of the lever is where the P force is applied and the other end of the lever is where this uh, uh, other this where the band will start from. Okay, and rest of the everything is will remain same. All right, so this is the extra portion which is added, and again the fulcrum point is O only. Okay, so it can move something like this. All right, or it can move something like this. Okay, so it will be pivoting about this point O itself. All right. So in differential band brake as shown in figure, the end of the bands are joined at A and B to the lever. So this band, again, this belt or band will be wrapped around this drum and they are coming in contact with this lever at point A and at point B. Again, if it is rotating in clockwise direction, so this side will be the tighter side and this side will be the slack side. So the tension T1 will be acting over here and this tension is at a distance B from this fulcrum point. This perpendicular distance is B. And this tension T2 is at a perpendicular distance of A from the fulcrum point. All right. Similarly, when it is rotating in clockwise direction, again, if it is rotating in clockwise direction, the tension T1 will be acting over here. That is, this will be the tighter side and it will be at a distance of A from the fulcrum point and the T2 force will be acting in this slack side and this force is at a distance of B from the fulcrum point. And again the force P is acting at point C which is at a distance of L from the fulcrum point. All right. So this is what is mentioned over here. Now taking moment about fulcrum point O, we'll take moment. So in this case, all the three forces will be producing the couple. Okay, so this point P, sorry, this force P, when the, let's take this condition that is clockwise rotation, it will try to turn this system in clockwise direction. This T1 will also try to turn it in clockwise direction and this T2 will try to turn it in anti-clockwise direction. Okay, so this will be in another side of the equation and rest two will be on the same side, that is PL plus T1 into B. This T1, this force T1 multiplied by resistance B is equals to T2 into A. This T2 multiplied by A. This is in the condition of equilibrium. So we can write this PL is equals to T2 minus T1, T2 into A minus T1 into B. So we have transferred this T1 over here. Okay. And for anti-clockwise direction, again, this P is acting downwards. This T2 is also acting downwards. These two produce will produce clockwise moment, and this T1 will produce anti-clockwise moment. Okay. So PL is equals to T1 into A minus T2 into B. Okay. So this is how we are going to calculate this. Now, in order to calculate the braking torque, as we have discussed, okay, in this case also there will be condition of self-locking and self-energizing. So as I told you, whatever force supporting this PL, okay, whatever force is supporting this direction of PL, that force will be taken, that force will help to apply the brakes. So that condition will be self-energizing, okay, as written over here. We have discussed this block brakes, same as we discussed in the block brakes also, that when the frictional force helps to apply the brake, it is called as self-energizing brake, right? In case of differential brake, we see from equations 1 and 2 that the moment T1B and T2B helps in applying the brakes because it adds to the moment P into L, right? So for clockwise and anti-clockwise rotation of the drum respectively. So when it is rotating clockwise, this T1 into B is helping the uh, braking system, and when it is rotating in anti-clockwise direction, this T2 into B is helping the this moment PL. So we have discussed that when the force P is negative or zero, then brake is self-locking brake. Thus, for differential brake to be differential brake and for clockwise rotation of the drum, the condition for self-locking is T2 into A should be less than equals to T1 into B. Okay. So when this will happen, what will happen? T2 upon T1 is less than equals to B upon A. So these distances can be manipulated as per our requirement. If the rotation is clockwise, okay, then what we should do, this T2 upon T1 should be less than equals to B upon A. Okay. And for anti-clockwise direction, this T1 into A should be less than equals to T2 into B. In case of anti-clockwise direction, this entire term should be positive. Okay. That is T1 into A should be less than T2 into B. Okay. Sorry, it should be negative. Then only it will be self-locking brake. Okay. So I hope this is clear to you. This is where we come to the end of breaking of topic of brakes. Now in the next class, we'll be discussing about the topic dynamometry. Okay. So I hope these are clear to you. So thank you for joining. Have a good day.